Hi, and welcome to Advanced Machine Learning. My name is Victor Banks, and right now we will deal with the so-called online convex optimization problem, which is, in light of our discussions about online linear optimization and online quadratic optimization problems, a quite larger class and important class of online learning problems. And we will ask for whether there is a suitable online learning algorithm which can also deal with this larger class. And the answer is yes, and we will see the online gradient descent algorithm as a suitable candidate for such type of online learning problems. So what is online linear optimization and online quadratic optimization about? Well, or how are they characterized? Well, they are characterized by the loss function. And we can derive a broader class of loss functions, namely the loss functions which are convex. And this is giving rise to the online convex optimization problem, where simply the assumption is the loss function with which we are dealing, which is mapping a pair of action and environmental data point to some real-valued number, that this here is convex with respect to the action component. So when we simply look at the function as a function of a, for some arbitrary z, environmental data point z, then this function is convex. So it has the typical convex shape if we would plot it with respect to a in the one-dimensional case, and in the two-dimensional case it has this bowl-shaped behavior. And both the online linear optimization problem and also the online quadratic optimization problem are belonging to this broader class of online convex optimization. Because this is the characterization we have due to the loss function. It needs to be convex with respect to the action component. But well, in the online linear optimization problem, assuming of course that we have a convex action space, this is always needed to say that a function is convex. But this loss function, the linear loss function, is definitely convex. So in the one-dimensional case it's simply a linear line. In the two-dimensional case it's a hyperplane. And another characterization, if we compute the second or the Hessian matrix with respect to A, we will end up with the zero matrix, which is positive semi-definite. And this is an equivalent characterization of convexity, that this is always positive semi-definite. Similarly, for the online quadratic optimization problem, which is characterized by a quadratic loss function, there again we can look at illustrations, see how the function looks like. So it has this parabolic shape. In the two-dimensional case it is bowl-shaped. Also we can compute the Hessian matrix, so the second derivative, and we will see, well, this is a positive semi-definite matrix for all the z's and all the a's we have there. So both of them, both these problems we have dealt with are in fact online convex optimization problems. So if we can derive an online learning algorithm which can deal with any online convex optimization problem, then it can also deal with these important specific cases of online convex optimization. The question is of course, how can we derive such an algorithm? So let's recall what we have done previously, where we have derived the follow the regularized leader algorithm in order to cope with online linear optimization problems. And in order to cope with them, we looked at the squared L2 norm regularization function, which is here. Yeah, so we are more or less penalizing actions which are having a large squared Euclidean length. And we derived, well, if we are dealing with a online linear optimization problem characterized by the linear loss function, which is the inner product of the inputs, we have, first of all, assuming of course that the action space is RD, otherwise we have perhaps to project onto A back. But in this special case, we have a fast update rule, namely we have that the next action in the next time step is given by the previous action minus eta times the most recent environmental data point. And of course, also relevant, we have derived a sublinear regret bound under some assumptions on the action space and the environmental data points. Now, the question is, why could we derive such nice things? Well, for the regret upper bound, we have to dig a bit deeper, but for the update rule, it's quite obvious. And it's somehow related to the nice form of the linear loss function, which in turn then also leads to the satisfactory regret upper bounds, which we used at one point, that we have this nice form. Because we can also rewrite the update formula by taking into account that the gradient of the linear loss function with respect to A is nothing else than the Z. So the linear loss function is A transpose Z. We compute the gradient with respect to A, only Z remains. So we can also look at the update formula and we realize that the ZT here is nothing else than the gradient of the linear loss function, the loss function we are interested in, where we plug in, well, the previous action and the current environmental data point. And if we have it written in this way, this reminds us a bit of the gradient descent, in the sense that for the next step, we are looking at the current step we are, or the current position we are, and we go into the direction with the steepest decrease, which is represented by the linear loss function, or the most recent loss function, because this is also depending on the ZT. And we go into this direction with the step size eta, which is the regularization magnitude we have. And this is exactly resembling the idea of the gradient descent, where we have as an objective function some function f we want to minimize, but here we have a loss function which is having these two components at the same time. So position, and here we are varying perhaps over the time. But essentially it's the gradient descent we are seeing here with this interpretation point of view. And now the question is, can we somehow use this idea of the gradient descent, which we see in the follow the regularized leader algorithm for online linear optimization problems, to have this update formula for another loss function, which is perhaps not the linear loss function, and preferably also having a satisfactory regret upper bound? And the answer is yes, if we have a convex loss function, because we can recall the first order characterization of convexity, which is stating that a function f is convex, mapping from S to R, if and only if, we assume that the function is differentiable, if and only if the following holds. So for any points x and y in S in the domain of f, we have that f of y is lower bounded by the essentially first order Taylor approximation of this function f. You see here. So if we would have a function f which is convex, and we look at some point at the first order Taylor approximation, which is a linear line in this case, then the entire linear line stays under the function. This is what this characterization is telling us. And well, we can also reformulate it, simply bring the fy on the other side and this linear term on the other side, and we end up with this equivalent characterization. Now let's apply this to the loss function, for which we know it is convex, and now assume that it's differentiable. So as a side remark, we can also derive something similar if the function is not differentiable by means of a subgradient instead of a gradient. But to keep things simple, let's assume that we have a differentiable loss function with respect to the action component. And now we can make the substitution. F is simply L with some fixed z, and for a and a tilde, or rather for x and y, we make the substitution a and a tilde, and what we end up with is, well, the difference between the losses, if we have a convex loss function of action a and a tilde, is bounded by this linear term here. So again, an inner product between the difference of a and a tilde and the gradient of the loss function with respect to the action component. And this holds for every a and a tilde and every environmental data point z. Now let's keep this in our short-term memory box that this here holds, and let's see how we can make use of it. So let's assume we have some sequence of environmental data points, can be anything you want, and let's assume that we have some online learning algorithm which is choosing somehow the actions a1 till at. And now let's make the following substitution or definition. Let's assume some artificial environmental data points, let's call them like this, z, t tilde, and they are corresponding to the gradient of the loss function with respect to a when we plug in the pair of action and environmental data point. And if we do this, we can derive the following. So if we look at the regret of this black box online learning algorithm, choosing the sequence a1 till at somehow, with respect to some competing action a tilde. This is by definition given as follows. So we have here the cumulative loss of the online learning algorithm, and we compare it with the cumulative loss of the competing action a tilde. And now if we use our first order characterization of convexity essentially, which leads us to this reminder box, then we can say, well, this difference here is definitely smaller than this inner product between the action at and the a tilde, the competing action a tilde, and the gradient with respect to a of the loss function L evaluated at the action at and the environment point zt. But we are having, or we made here this substitution that we simply called this thing here, a new artificial environmental data point. And well, we can use the law of distributivity, end up with here the difference between the inner products, where in both cases the artificial environmental data point comes into play. But this here, respectively, this here is nothing else than the linear loss function evaluated at AT and this artificial environmental data point, and here the same, simply with A tilde as the action and ZT tilde for the environmental data point, which leads us to this, that this is equal to the difference of the cumulative linear loss of this black box online learner for the artificial environmental data point, ZT tilde, compared to the cumulative loss of the competing action, where the loss is measured in terms of the linear loss and where we have substituted the environmental data point by the artificial environmental data points. So we have this regret upper bound. So we measure the regret with respect to some competing action A tilde with our target loss function, which is convex and differentiable. And we end up with, this is always bounded by the regret of the same online learning algorithm, but now with the linear loss function as the new loss function, as the upper bounding loss function, and another environmental data point. So a substitution for the environmental data point. So essentially we have now gone from a convex problem, we had here convexity, to, well, still a convex problem, but now also a linear problem. So where we have this linear loss function. And luckily, we know how to deal with an online linear optimization problem. Namely, we can simply use the follow the regularized leader algorithm. So what we simply can do is we could run the follow the regularized leader algorithm, and instead of providing it with the real environmental data points, provide it with these artificial environmental data points ZT tilde, and tell the follow the regularized leader algorithm that we are coping with the linear loss function. And then squared L2 norm regularization we have seen is a good idea. And if we do this, if we do this substitution in the update rule, what we get is what is known as the online gradient descent algorithm, OGD, where we have the following rule for choosing the next action. So with this, next action is equal to the previous action, which we update into the direction with the steepest decrease regarding the most recent loss, which is represented by the gradient of the loss function evaluated at the previous action and the most recent environmental data point. So this here is in fact nothing else than our artificial data point we have specified. And we go into this direction with a step size of eta. So this is again this gradient descent spirit we see here, and we have transferred it to the online learning world, and accordingly this is then called the online gradient descent. Again, we make here the assumption that the action space is RD. If this is not the case, then we have to project here, of course. So it might happen then that we leave the action space A with this update formula. What we do then is making a projection back onto the A space. And for the first action, once again, we have to choose something arbitrarily. All right, now we have defined and motivated the online gradient descent, and now we want to analyze it next time.